Okay, hi guys. So we're starting into learning target number 4. I can describe the acceleration of an object by interpreting graphical velocity, time data using math and computational thinking to correctly use equations of acceleration. Okay, so we've been talking about velocity last time. Now, today we're going to be talking about acceleration. So, first thing let's look at here, this is kind of like remember on the dot models that we looked at and we said that these snapshots are taken at the same time interval. And so we have 0 seconds, and then 1, 2, 3, 4. And you'll notice here on this one that the distance between them is the same, meaning they've traveled the same distance in the same amount of time. And distance covered per time period is velocity. So you can see that the velocity of this object is uniform. Okay, it stays constant. Now, our non-uniform velocity, again, we're taking these snapshots at the same time interval, 1 second, 2 seconds, 3 seconds, 4 seconds. But you see how less distance is covered over the same time interval? And so we have a change in that velocity. It's no longer constant. And that's how we define acceleration. Acceleration is a change in velocity. Now remember, velocity is a vector, meaning it's both magnitude and direction. And so here you can see if we're changing the direction, then we're also changing our velocity, even if the speed is the same. We're traveling the same speed here, here, and here. It's the fact that we're changing directions which changes the velocity vector, and that is also acceleration. So acceleration is a change in velocity, and that might look like a change in speed, or a change in direction, or it might be both, a change in both speed and direction. Okay, so our more formal definition. Average acceleration of an object is a change in velocity during some time interval, and that would be average. Now, instantaneous is what is in that very moment, that very instant in time, the change of velocity. Okay, so that's the difference between average acceleration and instantaneous acceleration. Now, let's take a moment and let's look at this graph here. I want you to notice we have velocity over time, or velocity per time, okay? And remember when we had the position versus time graph, and we realized that the slope of a position versus time graph was velocity? Well, what is the slope of a velocity versus time graph? Well, slope we know is rise over run. So if I took my rise, which is in meters per second, and I divided it by my run, which is in seconds, okay? So I'm taking meters per second and I'm dividing it by my run, which is in seconds. It's a little unit analysis here. Let's see, it'd be meters per second multiplied by the inverse, and that would leave us with meters per second squared. And that is units of acceleration. And so the slope of a position versus time graph is velocity, and then the slope of a velocity versus time graph is acceleration. So when I look at this and I have that idea in mind, we're going to look at this graph here, find the average acceleration of the train during the following time intervals. Okay, so our average acceleration for a time interval is the slope of the line over that time interval, okay? And so I want you to see, we have kind of our equation down here. So rise over run, or the change in my velocity divided by my change in time, that's what we have here. So that's the same thing as velocity final minus velocity initial divided by time final minus my time initial. Okay, and that's my average acceleration here. Okay, so if I take this equation that I have here, I'm just going to say, okay, velocity final when I'm looking from 0 seconds to 2 seconds. Well, my final velocity there is 8 meters per second. My initial velocity for that time interval is 0 meters per second. And then I'm going to divide this, and I could say that is 8.0 and 0.0. Okay. I'm going to divide this by time final, which is 2 seconds, minus time initial, which is 0 seconds. So we'd have 8 meters per second divided by 2 seconds, or we'd have 4 meters per second squared. Okay. So that's what we have for that time interval. And now we need the slope of the line from 2 to 5 seconds. Well, we see we don't have any change in velocity, right? Our velocity final is 8 meters per second minus our velocity initial, which is 8 meters per second. So on top of my fraction here, I have 0 meters per second. And so then we're going to have 5 minus 2, so 0 divided by 3 seconds. So it's still 0. So our acceleration here is 0 meters per second squared. Okay. Now when we look from 5 seconds to 6 seconds, okay, so we're going to say at 6 seconds, my velocity final is at 4 meters per second, and my velocity initial for this 5 second range was 8 meters per second. And I'm dividing that by 6 seconds minus 5 seconds. Okay, so this would be negative 4 meters per second divided by 1 second, or I'd have a negative 4 meters per second squared. Okay, now this should make sense because when I look at the slope of this line, I have the exact same slope here, only we have a positive slope and a negative slope. And now we want to figure out this last time interval there. So from 6 seconds to 10 seconds. Well, velocity final at 10 seconds is 0. My velocity initial at 6 seconds is 4. And then time final minus time initial. So it's a negative 4 meters per second divided by 4 seconds. So we have a negative 1 meter per second squared. Okay, so those are my average accelerations for those time intervals. Okay, so the change of rate of the velocity is the average acceleration over a given time period. So we have this equation here and we kind of extended it there. There's many ways that we could rearrange this, right? But let's look at some of the basic ways. If we wanted to solve for our change in velocity, then we would just take acceleration times by delta t would equal our change in velocity. Now we could throw in those deltas, those final minus initials, and keep working from there. Or if we wanted to solve for time, then we'd have delta t. And here's a common mistake that I see. So I'm solving for delta t. So I'm going to start by getting it out of the denominator here. So I'm going to multiply both sides by delta t. And so I have delta t times by acceleration equals velocity. And then I'm going to divide that acceleration. So delta t is actually equal to our change in velocity divided by acceleration. And we can ask ourselves, unit-wise, does this make sense? Does this work? And velocities are in meters per second. And we're dividing this by acceleration, which is in meters per second squared. Okay, and so I'm going to have meters per second multiplied by seconds squared over meters. Meters cancels. This s cancels with one of those, and we are left with units of seconds. Now, we have some thought experiments. But before we jump into that, let's do one before we get into this. I want us to take the simple situation of taking a ball and throwing it straight up into the air, and then the ball returns back to your hand. You catch it, okay? So we have this ball, right? And you throw it up, and it reaches some kind of peak, and then it starts coming back down. Okay? Now, let's establish an origin. Let's say this, your hand, like this moment that you let it go, we're going to call that 0. That's going to be our 0, 0 point, like our origin, okay? And we're going to call going up our positive direction, okay? And then going back down would be a negative direction. So, when I release this ball, I've thrown it into the air with some positive velocity, right? And because if it had a negative velocity, then it would have gone down, but it didn't, it went up. So our velocity here is positive. But think through this. We go really fast at first, right? The ball will go really fast, and then it gets slower and slower and slower and slower, and eventually it would stop, and then it would start speeding up faster, 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 faster. Okay? So our velocity here, our velocity is positive. And when we look on this side of it, our velocity is negative because the direction's negative. But what about the acceleration? Now, here's something to keep in mind. If your velocity and your acceleration have the same sign, meaning they're both positive or they're both negative, then that object's going to speed up. But if you have opposite signs, like your acceleration is positive and your velocity is negative, or your velocity is positive and your acceleration is negative, then they're counteracting each other and the object slows down. And so that's why when we throw a ball into the air, even though it has an initial positive velocity, the acceleration of the object is negative. Like, the acceleration is wanting it to bring that ball back to Earth. And so that's why it slows down here and then it stops. And now our acceleration doesn't change. Our acceleration is still negative, and that's why the ball speeds up as it hits the ground, because our acceleration and our velocity have the same sign. Okay. All right, so with that in mind, how can braking, like using the handbrakes on a bicycle, provide for both negative backwards and positive forwards acceleration? Well, let's think about it. We just talked about velocities and positions here. Let's start with this negative one. If my bicycle, we are headed this direction, okay, and then I slam on the brakes, my acceleration, so my velocity was positive, but then I pull on that brake, and so that acceleration would be negative, and so that would make the bicycle come eventually to a stop because we have opposite signs there, right? Okay, so I want you to think through this positive forward acceleration side of this, come up with an answer, and then when you head back to the next video, we'll talk through it together.